All right, good morning. How are you guys doing? I feel like the rain just kind of, rain yesterday put everybody to sleep this morning. It's a dreary morning. Yeah, seriously. Okay, so just a quick update for you where we're at. I revised the syllabus just a bit. Today we're finishing up kind of conversation on chlorination side of disinfection. Next time we'll get into UV and some advanced oxidation processes kind of stuff. Then we're getting into water softening. And on the 26th, I will be on campus, but I have to be on a call all day for a panel session thing. So I'm probably canceling this class unless I can find some sort of a substitution. If so, it might be some sort of a research topic, kind of a deal. So for the moment, that's a bit tentative, but I will probably have to cancel that one. I have a student that can guest lecture for my other class, so if you wanted to catch that, I could give you info, but I'll probably, if this is the case, then I will probably provide you some reading material, some stuff related to the Flint water crisis that we'll talk about after the exam as a activity to do in the meantime. Okay, but I don't think that'll interrupt us too much, so we're gonna get back to it with disinfection. Last time we left off kind of taking a look at a couple problems with, chlorine chemistry and kind of what that looks like in practice, how to get a rate constant and do things with all of that. Okay, so I'm going to pick back up here the new set of slides. Really, one of the concerns about chlorine disinfection, the reason we don't just say, okay, we'll just add in tons of chlorine, right? Because if we stop and think about a given rate constant, and we'll see this today, we'll go through this. The rate constant for disinfection is going to depend on the specific interaction between chlorine and the microbe, but it's also going to depend on how much chlorine we have there. So we could think to ourselves, well, let's just hit it with a lot of chlorine. But there's some pretty important reasons why we might not want to, and those are called disinfection byproducts. Well, cost also, but the disinfection byproducts are essentially, we have these organic molecules in water. They may be completely harmless typically. You see on the right there just some examples of what these might look like. That could be from soil, from plant material. You look into a body of water and it's probably not crystal clear. Sometimes you do. Sometimes you have crystal clear water, but usually there will be some color to it, right? I think even the background I have on my desktop here has some green water in the background. And that's colored because there's some sort of organic material in it. It'd be like making tea, right? Your tea leaves are letting these molecules get into the water, and that's giving it some color. So if we have a lot of that, and then we react it with chlorine, we may form halogenated organics. Now, that by itself is not necessarily bad, but there are a lot of halogenated products that end up with higher toxicity. So some of the functional groups, and sometimes if a molecule breaks down into smaller components, we can get things like trihalomethanes, haloacetic acids, and these, by the way, could be just some group on the rest of the molecule. So we can highlight just a little piece over here of this larger molecule. And so, in chemistry, we'll call the rest of it R. So the rest of the molecule bonded to, let's say, for the trihalomethane case, a carbon. And as a methane group, usually this is a methane, except that one bond goes to like the rest of the molecule. Or it could just be a methane, this would be methane directly, right? Either way, what happens when we chlorinate is we end up with a scenario where a trihalomethane now looks like this. So all of those hydrogens are now chlorides. That changes the nature of the molecule, certainly makes it a lot heavier, and they tend to be more toxic. So that reaction will occur during chlorination and things like it. So that's the type of scenario that we have some concern about, because we know these guys are not good to ingest. So then there's typically some sort of a balance between how much chlorine are we doing versus how much bacteria do we need to kill, all of that. So there are some scenarios where maybe in the summer months where there are more bacteria in a given body of water, the chlorine requirements are increased, and you might be pushing your limits a little closer. And this actually tells us something important about the chlorine contactor size. If we can use a lower dose of chlorine, but give it a longer amount of time, then we can achieve the same thing as a high dose of chlorine with a short amount of time. So that type of scenario means if we have too small of a tank, we need to overdose the chlorine, and we tend to form more disinfection byproducts. That was one of the problems, one of many problems with the Flint, Michigan river swap that ultimately caused the Flint water crisis. So we'll talk about that in a few weeks. But this is kind of the process. It could be other halides too. Bromide, iodide are also probably even more so toxic, but we don't typically use those for drinking water, or if we do, it's like a one-time use type of situation while you're hiking or something. Okay. So noticing that chlorine ends up reacting with stuff we don't really want it to, another issue that we run into is chlorine demand. So whether it's drinking water or wastewater, when we chlorinate, we have to recognize that some of the chlorine is actually going to be demanded by the other stuff in the water. So if we had oxidizable metals like iron, maybe Fe2+, could be oxidized to 3+, could be manganese, all sorts of things like that. Sulfides, so HS- or S2-, excuse me. So hydrogen sulfide and the different sulfide species there. Could all be oxidized towards sulfur, or excuse me, towards sulfate. Things like that can certainly demand chlorine in order to perform that oxidation, and it's just simply going to happen, and it's going to happen rather quickly. So one of the ways we actually one of the ways we quench chlorine if we're done with it and need to reduce it is actually adding sulfide groups, because each one, to convert it all the way to sulfate, which has a SO4 2-, that's like the S is in a +4 state or +6 state, it requires a lot of chlorine. So these can be pretty significant chlorine demands. Nitrogen is another example. So if we have any type of ammonia, like NH3 or NH4+, when we react that with free chlorine, what we end up with is a chlorinated ammonia, or we'd call it a chloramine. So in this case, we would end up with NH2Cl. We would call that monochloramine because there's one chlorine group there. So it's kind of a hybrid between the reactive chlorine and ammonia, right? It's actually a lot like looking at trihalomethanes, right? Except we're dealing with a ammonia instead of a nitrogen instead of a carbon. Now, once we have a chloramine, these can then continue to exert chlorine demand a little bit. So NH2Cl plus HOCl, well, sometimes or in part, this is actually a equilibrium reaction, will create NHCl2, which is dichloramine. And that will also be in equilibrium with trichloramine. These are not quite as abundant when we have chlorine in solution, but certainly that can happen. Okay, so then the chloramines, this is partly important because they're not as reactive. So sometimes we'll even use it as a residual chlorine where we want a little bit of chloramine so that it stays there and it keeps the pipes clean. But this is also the stuff that is really stinky and smelly and burns your eyes if you go swimming, right? So I don't know if I've told you this already, but if you ever go swimming and you feel like the pool has a lot of chlorine, it's mostly chloramines, right? That's what you're experiencing for the most part. So this is kind of the how it comes about. And the deal is when we are doing any sort of chlorination, what we're looking for, what we need to account for is all of these sources of chlorine demand so that at the end of the day, we know that we have the amount of free chlorine that's going to do the disinfection available to do that disinfection after all these demands. So we might say we'll have some amount of chlorine that we applied minus the demand will result in what we would call, and I'm going to describe this specifically as free chlorine residual. So that's the stuff that we rely on to do the disinfection because that demand happens rapidly. And so then when we want to give it a 20-minute contact time in our chamber, we can't count on that. So we'll call this our disinfectant or the effective disinfectant. Okay, so one way to take a look at the free chlorine demand and how to navigate some of these chloramine formation and things, we would call this breakpoint chlorination. Because if you take a look at what happens when you add chlorine, if you take some particular water and you add just a little bit of chlorine, okay, then you see, okay, how much do we have residual? Well, we can step it and say, okay, at 1 milligram per liter, we added, or 1 ppm, the actual chlorine residual is barely noticeable. So we bump it up to 2, and okay, now we have maybe 0.3 or 0.4 ppm residual. And then for a little while, it starts to increase pretty straightforward. We add 1 milligram per liter, we get, some amount, maybe half that. We get some response directly. So we're starting to say, okay, we're increasing our dose here. At some point, we end up having formed too many chloramines, and so then, well, let me pause here and say, if we look at the chart, oxidizable metals here. So early on, we get rid of that kind of stuff. This probably would include some organic molecules that are easily oxidizable. Then we're starting into the formation of chloramines. For a little while, we're forming this monochloramine, and then at some point, we're actually consuming chlorine, and I think I forgot to mention this, but chlorine can also potentially attack the chloramine and then just oxidize it to the point where we're getting the chloramine itself is being destroyed. So that reaction is demanding some chlorine as well. So eventually we have some amount of chlorine, some amount of chloramines, and then we have a straight curve. So this is what we call a breakpoint chlorination, or a breakpoint curve. At some point, we've broken through all that demand, and now we have a little bit of chloramine. Some of it's just been destroyed altogether, and then anything we add is now free chlorine residual. So for some time, we don't have much free chlorine because most of this is, or some of this is free chlorine, some of it's this chloramines. That goes back away, and then from here on out, anything we add is going to be free chlorine. Okay, so all that to say, if we need 5 milligrams per liter of free chlorine, it's not quite as straightforward as just saying, all right, let's add 5 milligrams per liter, right? Because then even if that happens to be at the right spot, a fair bit of that's chloramine, and that's not giving us 5, right? So in this particular diagram, we see in order to achieve that 5, we would have to add something like 12 milligrams per liter of free chlorine to achieve a residual 5 milligrams per liter. Okay, so there's some built-in costs there that we have to account for to achieve the chlorination as desired. All right, so let's talk about the kinetics of disinfection. This is what we'll use is a concept called contact time. This is coming from what's known as Chick-Watson kinetics, and this is really neat research from back around 1900. I don't remember if there was a Nobel Prize involved, but Harriet Chick and might have been Isaac Watson. I don't remember his name, but famous researchers in kind of the disinfection world. Some of the very early dose response type studies for bacteria. It's pretty neat work. You could find it today, and it's like looking at it as like useful math, but also like, oh wow, look, this historical document to look at it. Okay, so the concept here is that we have some concentration of chlorine, for example. Could be ozone, could be some other stuff. And then we have some amount of time in which it's allowed to contact it. So if you've ever done some cleaning with bleach and you have some difficult stain to remove, you might have put a lot of bleach on it and then given it time for that reaction to occur. And that bleaching reaction is kind of the same thing, right? We are oxidizing something to try to destroy it. I just noticed my video is off, so I'm going to turn that on. It's supposed to be on, so one moment. There we go. Okay. All right. So just like we've done in the past with our mass balance kind of stuff, we can describe a rate at which n changes, if n is our bacteria or our virus, whatever we're trying to destroy. And we can say that rate of change for n would be equal to, well, dn dt in some volume. But more specifically, we could relate that to a decay reaction, so minus K times the chlorine concentration to some dilution factor power times n to the 1 power. Now, one thing you'll notice here is this can get complicated if the concentration of the chlorine changes over time, or the disinfectant. So if the bacteria themselves were demanding a lot of chlorine, so there was a meaningful change in chlorine as the reaction occurred, this would effectively become a second order equation because it's dependent on the reactants in two different manners. Fortunately, we can typically assume that C to the N is constant because that we don't have a whole lot of demand there. If we use ozone, maybe that would be a bit different, but it's for the sake of chlorine and for the sake of this class, we're going to typically assume that that concentration is constant. Okay, so this N would be a number concentration. C would typically be something like milligrams per liter or millimoles per liter. The lowercase n there, this is called a dilution factor or dilution coefficient. If we have a well-mixed system or an ideal reactor, we can assume that's 1. A plug flow reactor is not well mixed except within the plug, so we would just call that an ideal reactor. Then this K is a coefficient of specific lethality, and now this guy is not like the typical K for a first order, because normally we'd have 1 over time for a first order reaction. If we take a look here, the K has to satisfy the fact that we also are incorporating the concentration here. So it has to account for those units in addition to the time units that are required. Because ultimately, the units here are some, if we add volume there, it's a change in the number per time. Well, let's just look at it this way. Number per time per volume, and N has number per volume. So the K normally has to just give us per time, but since we also have this concentration factor in there, it has to have the inverse of that particular concentration. So this K has to have liters per milligram if we're dealing with milligrams and liters. Now, that's our coefficient of specific lethality that's specific to this particular disinfectant and that particular microbe. So this will be different if we go from E. coli to Salmonella. It will also be different if we go from chlorine to ozone, for example. So this would be each disinfectant to microbe pair. All right, now for the sake of solving a problem, if we notice as we're doing our integration or as we're doing our mass balances one way or the other, we will see that if K is a constant and C is a constant, we could combine them, simplify a little bit, and say, hey, this is just one constant here, given our particular condition. So we could call this K star to say, well, K star would be K times C to the N power. Now here's where we get the per time units that we're used to. This could be per seconds. I'm just giving an example of per minutes here. Then this all makes sense like a typical reaction rate constant that we've always looked at. dN dt equals minus K times N. So that's the deal. This is, we would sometimes call this a pseudo first order rate constant. So effectively we have a first order dependence. Sometimes when we do a reaction that looks like this, the bacterium or the organism might be resistant for the first few moments. So we might have a little bit of a lag phase or something. But once progress starts happening, it's going to be first order with respect to the microbe concentration. And we assume that the disinfectant is constant. Okay, here's a bit of an example from some work I did as a grad student, where we had, in this case, some material that we were using as a light sensitized disinfectant system, where we'd shine light on the material would get excited and transfer its energy from oxygen in the environment to something called singlet oxygen, which is just an excited state. And this stuff would be acting a lot like ozone. This happened to be C60 or fullerene materials. Now, in this case, what I was changing was the amount of the light sensitizer. And so if I had more of it, then we get more single oxygen. And so if we had a lot of it, our kinetics are really rapid. We see that right there. That was the case for 1 micromolar of this stuff was giving us a very rapid disinfection of these viruses. These were viruses that infect bacteria. And that was on the order of like 2 minutes. We had like a 5 log reduction. So this is log versus time. If we didn't have much of the material at all, we kind of had nothing over the course of an hour. And we can kind of see that, you know, there's some dependence on that concentration. Something kind of funny happens with this one where we probably have some other factor affecting the kinetics, but for most of these we see that it's something like a linear line depending on how much of our disinfectant we have. So the more we have, the faster it goes. Okay, so let's do an example. We have data here. This is data for HOCl disinfection of poliovirus at a concentration of 1.8 milligrams per liter. So that's 1.8 milligrams per liter of HOCl. Shown below, the temperature is 20 degrees Celsius, the pH was 6. Determine the rate constant of inactivation, assuming the Chick-Watson model applies with an N value of 1. Okay, so there's something we could do that is a little bit more complicated, and then there's a way we can do this that's a little bit more straightforward. Last time we were talking about chlorination, we looked at the amount of chlorine fractionated to HOCl versus OCl minus, right? So, and we're going to get to a lot more of that kind of stuff when we get to water softening, because there's a lot of those types of reactions. For now, we will just read this problem in a particular way where we don't deal with that, because it's a little bit vague. It says 1.8 milligrams per liter of HOCl. Now, HOCl is usually what we want to disinfect with, but it also gives us a pH and a temperature, meaning we could solve, you know, we could assume that the Ka is 10 to the negative 7.54 at that temperature or something close. And we could say the total chlorine is 1.8 milligrams per liter, and then solve for how much is in the HOCl, you know, do all that. But instead, what I'm going to say is let's assume that all of the, you know, this 1.8 milligram per liter is just all in HOCl. Instead of assuming that the total chlorine was 1.8, we're just going to assume that, and you can kind of read it this way too, like it, you know, it's vague enough where I could see it either way. So let's just assume, skip that step. We've done it before, we've done practice. Assume that we have 1.8 milligrams per liter of HOCl, then solve for that problem. Now this will require either Excel or a graphing calculator or something to that effect to get a line of best fit, or you could plot it out yourself and kind of make an estimate. But give this a few minutes, and I will kind of sketch up the process on my end as well and walk you through how I would tackle this. But this is an opportunity to take the data and go from the kind of experimental data to a rate constant. guys got an answer? Let's see how you did. Okay. Anybody need a moment more to get in? Okay. All right. So just one question, and it is, you know, give me your answer here to what you, basically the closest match to what you found. And then we'll go through it. So this is, you know, just a participation activity, basically. All right, so fair bit of you got it wrong. I think that the blue answer is, let's see, I can't remember exactly, but I think that's maybe something that it was close to, but not quite the right process. Okay, so don't worry too much about that. You know, the nice thing is I know who's like here and engaged in class, right? That's kind of what I'm using it for. So hopefully that also gives you some impression like, hey, have I connected all these dots yet? So I'm gonna work this through with you. I've got it, I have it shown in Excel as well, but I'm gonna kind of sketch up the process here first. So first of all, we could imagine plotting this data, which maybe you did, with time versus this number, this plaque-forming unit number. At time 0, we had, let's say this is like 6,000-ish up here. We've got 0 and time up to, let's say, 8 seconds. Okay, so we start somewhere up here. At 2 seconds, we are at about half that. And at 4 seconds, excuse me, we are less than half of that. By 6 seconds, we are down to 700. And 8 seconds, we're at 300. So it probably looks something like that. And the key thing here is to recognize that that's not going to give us a useful straight line, right? You could maybe get a program to tell you, okay, well, what's the fit if we assume that's exponential? But the more convenient thing to do to relate a rate constant, so let's take a step back and say what we're looking for is dn dt. We know that in this scenario, we just have this inactivation data with a Chick-Watson model applying with an n value of 1. We're not given much else about it. So one thing that's not too super clear here is that this is essentially, because it's n value of 1, the disinfectant is well mixed in some regard, is kind of the assumption. And we're given a time dependency, so we're not in like a steady state scenario where we have no accumulation. We do have an accumulation. We're not given anything about any flow rates or anything. So essentially, we assume this is a batch reactor. That's actually very typical for when we do some sort of disinfection study. So we'll have some volume. We're looking for what's happening in here, and we describe that as this k that we're trying to solve times c to the n power times n to the 1 power in that volume. So we would cancel the volumes. We do pretty much what we do and have done many, many times. Separate these, integrate them, remembering that c to the n is a constant and n is equal to 1 there. So c is going to be 1.8 milligrams per liter. And really, we just need to solve for k. So what this looks like is, as we go through the derivation, we will get to the natural log of n over n naught equals minus kct. So when we take a look from this perspective, one thing that we can do is say, if we can plot this, then we have a time-dependent graph of n, and we have the data for n. So if we were to plot the natural log of c over c naught, or excuse me, n over n naught, on the y-axis, and then we could either do time, or more conveniently, this contact time circumstance, and say c times time. I'm just going to put a dot. Then what we're left with should be a plot where the slope is k. And it should look a lot like this, where this actually would be 0, and we're going a little bit negative. And we should have some data points that we can plot a straight line through. And here's k. Now, there's several steps in there in order to get to that point, but we kind of have taken a look at this type of thing before. Maybe we didn't look at raw data and converting it, but that was kind of the plan, or the approach that's probably best to take. Does that make sense? Do you guys, how close did you get to that? Anybody linearize it with the natural log? Okay. So that's when we're trying to extract kinetics like that, a lot of times that's what we need to do. Now, if it was a zero order reaction of some sort, we could just take the raw data and then take a line of best fit. But because we have to have that natural log dependence, that's what we have to do. So I put in the data here that we had from the problem. And then the next thing I did was I said, well, let's take the natural log of that data. So the natural log of what we started with, or where we're at in the current moment, divided by what we started with, right? So at time 0, it's just that 6,000 divided by 6,000. At time 4, it's this 1,200 divided by 6,000. So I froze one cell to just stay there, and then we carry that down, and we see that becomes negative as we go. Over here, we could have just done time and then accounted for the, we'd have to divide our answer for the k by that 1.8 milligrams per liter. That would be fine as well, but I went ahead and just inserted that to put the x-axis as concentration times time. So this is seconds times milligrams per liter. Then we can plot that. So if I did it just by time, it looks like this. And if I did it instead of by time, I did it by contact time. I'm gonna delete that. Then it's kind of the same deal. The data will look very similar. It's just on a different x-axis, right? So then we can take that y value there, and that's, or excuse me, the x value, so y equals mx plus b. There's no plus b here because we're forcing it through 0. So that's our rate constant, the slope there. The other case here, this is 3, 7. It looks like that's the answer that most of you put on the Kahoot. Did you find that answer? Anybody? Yeah. Okay, so that might be why some of you had that. So the only added complication is that concentration as well, factoring that in. Does it make sense now that you're seeing it this way? So you feel like you could do it again if you had to? Okay, good. All right. Okay, so we can go ahead and get into some UV disinfection then. That'll kind of help keep us on track, I think. So UV disinfection is largely about causing DNA molecules to end up what we call it as dimerizing. So a DNA molecule is a lot like a zipper, and you have some sort of enzyme that unzips it so that you can bring in new material and make a new one, right? And it's going to be zipping and unzipping in order to replicate, in order to do processes. And if something needs to read what's in the DNA, it's going to be like a little train going along the tracks, right? So there's going to be a lot of dynamics relying on the DNA to be in that helix kind of ladder-like form. What happens if we expose it to UV light, specifically in a particular range, is it's kind of like adding superglue between two pegs of the zipper. Two of these molecules that are like the base, you have base pairs. Well, two of these bases can dimerize together on one half of the zipper, and it would be like if you put some superglue on half of a zipper. Then you try to zip it up, and you can imagine you're going to get stuck, right? I haven't actually tried it, but I've had enough zipper problems with jackets and things that, you know, if there's a problem, there's a problem, right? And it's frustrating because it's like, how is this entire piece of clothing ruined by this one little thing, right? So in order to understand that, we ought to take a look at our electromagnetic spectrum. So visible light, typically we say is between 400 and 780 nanometers. Now what we're talking about when we say nanometers, light acts like a wave and a particle. So if we look at a wave and we have the distance between two peaks or two troughs, that's the distance we're talking about. And so 400 nanometers is the lower end of what our eyes can see, and that's pretty much the violet range, violet, deep blue. All of this is a bit of a spectrum, so we probably have a little bit of variation between what you or I could see in different ranges in terms of color. You know, some people are colorblind, so there's some things with that. But generally, once we're down into the UVA region, we can't really see it directly. We might see some molecule that's excited and then emits some light or something. We might see that light. UVA, we define just categorically between about 315 nanometers and 400. This is the stuff, this is like black lights, right? So you probably don't want to stare at them directly, especially if your eyes are used to the dark. But they are generally not too hazardous. They could give you a skin tan. If you spend a long time in it, maybe you'd get a sunburn. Generally, we get a little bit of UVB from the solar spectrum. I could pull up a slide, but the solar spectrum is going to look something like this, and it's all kind of crazy. But what reaches the atmosphere in terms of the ultraviolet light, we have a decent bit of UVA, although not nearly as much as we have visible light, and we have just a tiny bit of UVB and practically zero UVC. Which is a good thing because UVC is that stuff that causes the DNA damage directly. UVB is the stuff that they're pretty high energy photons, at least compared to anything else we get from the sun through our atmosphere. So that's the kind of stuff that really is in the burn territory. UVA can also do the burn. Visible light could burn you in some ways, right, if you have enough of it. But typically what we're dealing with here is UVA and B are starting to cause molecules to go through this excitation to create some sort of radical species. This is actually what I was showing you with that data on photosensitizer disinfection stuff. Some of our molecules will create oxidants that can then go and react with something. It could be DNA, it could be protein, lipids, whatever. So if you have enough of that type of reaction, you will get a burn. That's actually why how skin pigment works is it quenches those excitations. It absorbs the light without creating excitation. And so sunscreen is an artificial pigment that way. It's not colored in our visible range, but it's certainly highly colored in the UV range. So that's actually how our like melanin in our skin, kind of how it works and how it's protective. That's also why our bodies, if exposed to UVA, tend to be triggered into producing more of it. Okay, so the UVC stuff then, that's the germicidal. That's what we're usually going to use for disinfection applications. As an example, if you take, you know, some people say sunlight's the best disinfectant, which is probably close to true if you're out in space, where there's no atmosphere to absorb all that UVC. It would be pretty harsh. But if you were to take, let's say, the SODIS approach, which is solar disinfection, you take a bottle, let's say you take a clear plastic bottle that lets the UV through. This one probably wouldn't work so well. And you put it out in this hot sun in the middle of Louisiana summer. It's still going to take 6 to 8 hours before that is anywhere, you know, if you had dirty water, before it's anywhere near closer to acceptable to drink. You'd get maybe a 2 log inactivation of most of the bacteria in there. That's not very good. But if you were to take germicidal range UV, you can have a few seconds of it and get the same result. It all depends on how much light you're using, but it is much more effective because it's a direct DNA damage type of approach. If you go below that, you're getting to the point where you really have to be in a vacuum in order to emit or transmit any of the UV. So it's really absorbed very strongly by anything in the atmosphere. And beyond that, we get to X-rays and so on. Okay, so what does it typically look like in practice? Well, there's a couple of ways for conventional treatment. Conventionally, we have these mercury fluorescent lamps. In fact, if we look at the lamps above us now, those are also going to be mercury vapor fluorescent lamps. So it's very similar to what's in there, but these guys have a coating around the edge, around the outside of the glass, that will absorb this UV light, because they are producing UV light, will absorb that light and then re-emit it back as white light because it's fluorescing. Okay, so a UV lamp that's not designed for the fluorescence aspect would just be a mercury lamp that we have this arc discharge, it excites the mercury. Maybe you'd also still call that fluorescing, but I guess this would be like a double fluorescence. There's also, by the way, the glass that they would use in this and the plastic and that white coating would all protect us from the UV. So we're not exposed to any UV from this. Maybe, you know, and I think they would have to use a fancier glass even to get the to get it to transmit through anyway. So the only similarity then at the end of the day is that if you break one of those, you have mercury vapor in the air now. You probably should clear out until that dissipates. Same thing with these UV lamps for disinfection. You don't want to break them because there's mercury, and they're, you know, reasonably expensive. And if you've ever been in classrooms like this, if you look around, you notice, okay, this one's pretty bright, that one's not so bright, and you know that one over there is, you know, having a fit and dying, right? They're not the best lighting inventions in the world, right? They have a set lifetime, and then we also have an added complication of, well, we have to protect them because it's very, you know, fragile. and it's hard to make some material that can protect them and also let light through. So we have to do it with a very fancy quartz sleeve. So it has to be very special glass quartz in order to let that light through. And when I say that light, typically these are, mercury has a characteristic signal at 254 nanometers. It works great for disinfection, but it doesn't transmit very well through anything but fancy, fragile, expensive quartz. So in order to protect these, we sheathe them typically, like in this reactor example here, we might have water flowing in here and then out there. So it has this time where it's passing this light, but that light is then encased in a quartz sleeve, and then there's an added complication of what happens when that quartz sleeve gets dirty. You can imagine this high energy light happening. There's probably some photochemical reactions occurring on whatever happens to be in the water. Even though it's pretty clean, maybe it's mineralization, maybe it's organic matter getting fried and just kind of sticking on there. Over time, it will build up it'll foul, and you have to take that quartz out and clean it. And this is actually a major expense for wastewater treatment plants and water treatment plants that are using UV. It's very likely that in that cleaning process, they'll break sometimes. It's labor intensive, and then it's capital intensive in terms of when these break. So that's a pretty big challenge. There's been some ideas of, well, maybe we can put these lamps on the outside and then have some kind of a clear chamber in there. This would really only work if you get the ability to use some sort of a fancy plastic that might be able to transmit. Maybe it's disposable and you could reuse it. That's more likely an option if we can move the wavelength to a bit higher. And I'll talk a little more about that in a moment. Okay, you might have seen UV lamps around if you've been into some laboratories. There are biosafety cabinets that will very often have a UV lamp to help keep the area sterile, free from any organism that might contaminate your working environment. These, you'll notice sometimes they'll be on if the sash is closed. It turns out the glass on that absorbs the UV so strongly that none of it makes it through. And I've tested this on multiple occasions because I work with this kind of stuff, and we have some radiometers to test that. And sure enough, that glass is quite protective. Okay, so been talking about the numbers a little bit. Here's those numbers on a graph. So the typical UV lamp that we often talk about is a low pressure mercury lamp. It has this very strong peak right here at 254. And you'll notice that if we were to estimate the absorption of light by DNA, that's essentially this germicidal effectiveness curve right here. So we can see that that UVB range was 280 to 315. We get a little bit of that from the sunlight, and DNA absorbs some of that. So some of the photoreactions that cause direct DNA damage can happen from that light we get from the sun, but it's just a small amount of it. And if we had a plastic bottle in the way, that UVB stuff might be absorbed anyway. So in terms of like effective solar disinfection, it's not great. In terms of protecting ourselves from it, if we had a long day in the sun and we expect UVB exposure, maybe a bit of protection is warranted, although I think we tend to overdo it a little bit in terms of the UVA portion, which might actually be some health benefits there, and not just, not just all protection all the time might not be the actual best thing. Anyway, that's just an opinion. Don't take that too seriously. Okay, but one thing we can see is this germicidal effectiveness. We have room. We could maybe hit 265 or something. Might be even slightly better than this, but we could even go as far as around 280 and have good effectiveness in terms of the UV absorption. And as we travel to the right, that's lower energy photons, so they can probably be less expensive overall. And they can transmit better through water, better through plastics. So we might have much more options if we can shift that curve. Mercury lamps, we don't really have too much we can do. The other type of mercury lamp would be medium pressure. They have a big peak out here towards the UVA range, a decent peak here in the germicidal area. It's just a little more spread and mushed, just given how that works. But these are kind of the two conventional ones, and you can see there's some studies on this germicidal effectiveness literally by DNA absorption from different organisms. So what they compare is, okay, how effective was the dose, or excuse me, how much light was absorbed by the DNA at different wavelengths, and we can kind of see that shape come up. This MS2, that's a virus. That's actually the one I showed you a few minutes ago, and this C. parvum, that's Cryptosporidium parvum. So just a couple examples of DNA from different organisms. DNA is similar enough that it's, even if it has a different arrangement, it's made up of the same stuff. So it's not going to be too different from organism to organism. Okay, another way to estimate that, here we have inactivation rate constants relative to kind of the standard at 254. So some will be a little better. 254 will be right at 1. If we go too far left, it's not becoming very practical, and you can see it's really dropping off pretty hard as we're getting to the point where maybe we get a little bit of this in the sunlight, right? Okay. So how does it work? And I have some notes from last time here, sorry. But the mechanism, I talked about it a little bit. This dimerization occurs where we have two, especially the thymines. If we have two neighboring thymines, that DNA absorbs light. Those particular groups are likely to react with one another and dimerize. That's the superglue component that I was talking about. Dimerization is really coming from the Latin words, so di meaning two, mer meaning molecule. So we're making, we have two molecules and kind of making them into one, sort of a thing. You can then recognize as an enzyme is coming through to read it, it's going to find this spot, whether we're replicating or splitting or whatever, and it's going to end up getting stuck. And unless the cell can repair that, this portion of the DNA is effectively no longer usable. So you can actually have a scenario where you can have a living organism, but it's unable to replicate. So it's been sterilized, but the actual organism is still alive. It won't, it'll only live for so long, but that is a possibility. Okay, another look at it here, and we see the DNA dimerization between these two thymine groups. A little more technical of a graphic. Okay, so what do we consider when we are talking about UV? What are the factors we need to think about? Well, all of it's about light dose. So anything that could impact, reduce, affect this light dosing is something we want to consider. So, for example, if we have a UV lamp and then we're trying to kill a bacteria, but we have particles suspended in water, well, those particles could scatter the light, could shield or shade the bacteria. The bacteria could even be stuck inside or on the surface of it, and then that shading or shielding, maybe the bacteria works its way inside of a particle, depending on what that particle looks like. So there's, actually that's shown right here, right? So there's several ways where particles can cause a big problem, right? If there's just a lot of organics, not even particles, maybe those organics are absorbing the light, so it can't even quite get there. So here's a few to do with particles themselves. We generally try to have some sort of filtration or particle removal before UV if we're going to use it. And the same thing's kind of true for chlorine in the sense that you could have these particles shielding bacteria directly like that. So that's kind of true generally, but UV is also especially sensitive to anything that will scatter this light. If you don't have the UV light submersed, and you just have it suspended above the water, you can also have reflection of light. And there's a few factors like how far is the light going through, how much light is there, a few factors like that that we need to consider. And a fair bit of that can be captured with what's called the Beer-Lambert law. If you've done any sort of general chemistry, you've used this even if you may not realize it. Anytime we're doing some sort of spectrophotometry, we're using a UV-Vis absorbance spectrophotometer, you'll have a little cuvette. What we're looking at is, okay, how much light is being absorbed by that solution now that it's some fancy color that we can use to measure our concentration of something. But the other thing that tells us is we can do the same thing to see how far the light will go given some water. Right, so in the lab, we know exactly what distance, and we're just trying to solve for maybe the concentration. In the case of a water treatment facility, we probably still have a known distance that we want the light to go to. So either we're asking, does it go that far, or how much of the light goes that far? Rather than solving for the C, we're probably actually looking for the final compared to the initial intensity of the light traveling through. So this dependence, it depends on the absorptivity given some molecule at a wavelength. That could be the molar absorptivity at some wavelength, lambda. Given some concentration of whatever kind of organic matter. In this graph down here, we see, I don't remember what USRNOM stands for, but SRNOM, that's Suwannee River Natural Organic Matter. Don't remember what river that is. But two different river waters, we see the organic matter that happens to be in them absorbs light with a profile that looks like this. So we could say, well, one of them, if we look at the kind of the 254 mark, one of them absorbs a lot more light there, and so our UV light is going to be less effective in that one because it will attenuate, and we'll just have simply less light through to the end of our system. So that brings us to, okay, well, how do we quantify light and dosing in a disinfection chamber? Well, it's going to be almost exactly the same thing as our Beer-Lambert law, or excuse me, as our Chick-Watson's kinetics, except that instead of a concentration, we have an effective light dose. So the dosing here, and I'm just following the convention of one of the books on this, we see this rate equation, how the number of bacteria or whatever is changing, given some dose and rate constant combined, right? This would be like saying K times C. So this guy here, what is this Greek letter, by the way? Is this capital gamma? I'm not up on my Greek life stuff. Anybody know it? I feel like I should. I always am like slightly embarrassed sometimes when I'm up here. I'm like talking and I'm like, this is alpha, right? I'm like, not sure. Okay, we're just gonna call this a K. Okay, so this is the coefficient of specific lethality for light of a given wavelength. It's probably capital lambda. I don't know. No, that wouldn't make sense. At any rate, this is just like the k we were talking about, where it was k times c, except this time it's k times the intensity of light that has that the solution has received. So then we can say this germicidal intensity would be the combination of those two. This is like saying k star equals k times c, right? From our former example, the Chick-Watson example. So overall, the dosage is intensity times time, just like the dosage of our chemical disinfectant was contact time or concentration times time. Right, so these are very analogous. It's just a matter of, do we have light that's doing it, or do we have some concentration that's doing it? All right, so a little bit more about that. We could say dosage D, that's intensity, the average intensity times time. Typically, we're going to talk about this in millijoules per area, so millijoules per centimeter squared, or maybe joules per square meter, something like that. Sometimes we might call this fluence, the intensity times time. So that's the sort of the flux of photons in some sense. Okay, so we will take a look at this next time as kind of an example problem, but that'll be it for this time. I think I'm actually a little ahead of schedule somehow, so all right. We'll leave it there. I'll see you guys on Tuesday next week.